Elon Musk SpaceX leaks new rocket engine design that could revolutionize Mars travel in just 39 days. Gone are the days when a mission to Mars was considered science fiction. If we go by NASA, it would take around 7 months. But that's just too long for Elon Musk. In today's video by Fly Me to the Moon, we'll discuss SpaceX's new rocket design that could revolutionize Mars travel in, get this, just 39 days. Yeah, you heard right. So let's launch this video. Science fact has just caught up with science fiction. While covering millions of miles in just under a year is okay, SpaceX has taken matters from not bad to wow. What is SpaceX's new technology to achieve this reduced travel time? Do you know the principle of how conventional rockets operate? Conservation of momentum. The low speed should be sufficient to launch something as heavy as a rocket into outer space. The fuel used in traditional missiles facilitates this downward momentum. To be more specific, liquid methane heats and expands upon adding an oxidizer to it. What happens when you release air from an inflated balloon? It moves up with a funny noise. This is very similar to the operation of a rocket. All that rigorous combustion at the bottom forces its top to move sharply upwards. If we were to explain this in a more geeky term, the upward pressure the rocket exerts is equal to its downward momentum. But alas, there is a limit at which the missile can be propelled merely by burning fuel alone. So to reach a greater height, you've got to burn more energy. If one plans to move a rocket into outer space without keeping fuel reserves in mind, they only set themselves up for failure. Wah, wah. Remember the 7-month time we spoke about at the beginning of this video? This is the principle responsible for the longer period. Now, ionized engines rely on electricity for increased propulsion instead of fuel-based conventional rockets. They produce ions that are driven through electromagnetic fields. The momentum required by such a system depends on the amount of electricity at hand. But that's not to say that ionized engines don't need fuel. It only means that the fuel requirement is significantly reduced. Additionally, ionized engines operate at 90% efficiency, as opposed to conventional ones, which have a limited efficiency of about only 35%. So what do you think? Is ion-based rocketry here to stay? Let us know your thoughts in the comments section below. And consider fueling up that subscription button. Once you do that, you'll find a bell icon right next to it. Click that too. Now let's head back into all this cool science stuff. Speed may be increased by 11 times using ionized engines. This results in less fuel use, making it even cooler. Ionized engines have been used in the past, more so like substitute players in the game of soccer. They were used in NASA's Deep Space mission, which used an N-Star ion engine to stabilize its satellites. If you think this technology is a recent discovery, you're in for a shock. Soviet satellites have used this technology from 1972 up to the late 90s. The ones they used were different Hall effect thrusters. These are also used to maintain the orbit of the Chinese space station. They have a really impressive track record too, surviving about 8,240 hours of continuous operation. So far so good, right? Like with every invention, ionized engines aren't flawless. Ionized engines use inert gases as fuels, ensuring particles can be propelled at high speeds. But all of that is in vain, as there aren't many inert gases available. As a result, the push is feeble right now. This is a huge deal, as greater propulsion is required to escape the Earth's gravitational field. That calls for additional propulsion tactics. Because of this drawback, its application is currently limited. While they are ideal for long-distance missions and propelling tiny satellites, it would take considerable time before favoring the fancies of Mars-loving humans. Ion engines operate by building circuits. These circuits are comprised of electrons in motion, capable of producing electric and magnetic forces. These circuits are more like feeble fences, as the atmospheric ions easily alter their equilibrium, and this poses a risk to sustained acceleration. Additionally, the chemically inert xenon used as fuel in these engines is ridiculously expensive. We're talking about $1,000 for a kilogram of xenon. Woo! You thought gasoline was high. But that isn't to say that ionized engines aren't being considered. The European Space Agency and the Australian National University are using their best brains to build a revolutionary ion thruster called the Helicon thruster. In addition, some ion thrusters in the works are suited to use multiple fuel sources to aid propulsion. An example of this is the magnetoplasma-dynamic thruster. The fuel options include hydrogen, argon, ammonium, or nitrogen. To add to its benefits, it can sometimes use the air in low Earth orbits as fuel as well. The Vasmir variable-specific magnetoplasma rocket can utilize this property. In other words, this rocket is not a picky eater. Although it prefers argon, this rocket is open to other fuels. And it's worth noting that it likes argon over its expensive counterpart, xenon. To add to all of this, Vasmir is considered more powerful than the other thrusters we spoke about. It is this gem SpaceX dreams of using to take humans to Mars in about 39 days. While all that seems pleasing to hear, it would still take considerable time before that dream would become a reality. For starters, the Vasmir is a high-energy thruster. Its plasma needs to be heated to a temperature of about 173 times that of the Sun. Ooh, that's hot. 1 million degrees to be precise. Even if we manage to do this, space alone isn't enough to sustain this bad boy, at least not to make the journey possible in a short span of 39 days. But that isn't to say that ionized engines are going to stay out of the books of space transportation. Their drawbacks are being taken care of by the big brains of the rocket world. Who knows? There might come a time when we can take vacations to Mars and dine with its inhabitants. With all that being said, chemical rockets are still the go-to for short-burn, high-thrust missions. Turns out Elon Musk is one of the many people behind the scenes aiming to make interplanetary travel possible. NASA's right behind. It aims to make the dream of stepping on Mars come true using nuclear thermal and nuclear electric propulsion. It claims to do so in a short travel span of 45 days. NASA and the Soviet space program have studied the technology for decades. In another endeavor, NASA has developed a system utilizing NTP and NEP, promising a travel span of around 100 days. Add a bimodal nuclear propulsion system to the mix, and the span of travel is reduced by 55 days. This idea, presented by Professor Ryan Gossi, was given a green signal and is one of among 14 projects chosen for Phase 1 development. If we keep everything aside and talk about matters from a realistic standpoint, it would be about 3 years to get to Mars. If we were to make use of existing technology, that is. Imagine being stuck in transit for 3 whole years in a spacecraft. Ugh, how much luggage would one have to carry for a 3-year trip? Seriously. Also, given the distance between Mars and the Earth, these missions would only be practically possible sometimes. They would be feasible only once in 26 months when the planets are closer in proximity. More reactor designs are in the works. These would include a power source in addition to aiding propulsion. A classic example of this would be the hybrid fission-fusion reactor chosen for Phase 1 development by the NEIC. And with that, Fly Me to the Moon calls it a wrap on today's topic. Yeah, we are astro lovers, and the news that a ticket to Mars might be a reality thrills us. But we're curious to know if it's the same for you. So engage with us and share your thoughts in the comment section below. Also, check out all the other science-y videos on this channel. And remember to subscribe, like the video, and ring that bell icon for more news in astronomy. Bye-bye.